Okay, equations. Quadratic in form. These will not be quadratic equations. They will be more difficult equations, but they will be quadratic in form in the sense that I can replace them by a quadratic equation. So again, I'm on the same page 185, and I am going to pick. So we are here. I'm looking at these problems, 41 through 49. Let's say I'm going to pick 48. I'm picking even number problems so you can work on the odd number problems. X to negative 2 minus x to negative 1 minus 6 equals 0. Is this quadratic?
Sure looks like one.
Absolutely not. A quadratic cannot have power negative 2. A quadratic has power 2, power 1, and no power. It can, or just a combination, right? Or just one of them, x squared. Or just two of them, x squared and the number. But no, this is not quadratic. Okay. I hope that I can replace it by a quadratic equation. So I'm going to look at these two powers and say, let's see what happens if I denote or substitute or denote x to negative 1 by any letter you will prefer. Give me a letter, not x.
H.
Okay, awesome. H is good. Now, if I show that this piece can be replaced by h squared, then I'm in business. And then I'll say this equation is quadratic in form, but I have to make sure that that's true. So if you square this, do you get this? Copy the base. Okay, let's see it. If I decide to square x to negative 1, what do I get? Copy the base. What do I do with the exponents?
Add.
Negative 2. So can I denote this by h squared since I denoted this by h?
Yeah.
Can anyone dictate the new equation that we just came up? We just made this up.
H squared minus h minus 6 equals 0.
Right. So I would say that this equation is quadratic in form. It's not quadratic, but it can be replaced by a quadratic equation. And this makes my life so much easier. Then even looking at this hurts my eye, right? So once I change this into this and find h, then what do you think I'm, yes, Tom?
I did just a quick thought for when this.
Please.
Okay, so I don't know how much you guys know this. I'm going to assume you all know this, but whenever you have a negative exponent, it's safe to assume that it's equal to 1 over whatever you have raised that negative exponent.
Correct. I will get to that in a second. You're right. So the property that Tom is referring to is this. A raised to a negative power is 1 divided by a raised to the positive power. It's just another way of writing a fraction. Well done. Okay, so now this is indeed quadratic, and I have 4 methods of solving it. Will I complete the square? Will I take square roots? I can't. Will I factor or quadratic formula? If it takes like this to factor, let's factor. Very good. And?
She said h plus 2.
Sorry, I didn't hear that part. Sorry.
Oh, no, that's okay.
Good. So there are 2 options for h. And they are?
3.
This is good, but it's not good enough. Why is not good enough? Yes, please. Because I solved for h. Well, this is our invention. But the equation is given in x. So I have to solve for x. So h equals 3 changes into another equation, and h equals -2 changes into another equation. Which equation is this?
Now, assuming, given that h is 3, 1/9 over, well, no,
What do I replace h by? What was h? Awesome. X to -1 equals 3. What is the second equation I have to solve? We'll come back to the first one in a minute, but
x to -1. Let's see.
very good. Thank you. Good. So as you said, x to -1 is what?
1 over x.
Awesome. And this is 3 over 1. And we know what to do. What type of equation is this now? Please don't say linear. Don't say quadratic. Don't say radical. Don't say with rational exponents. But thank you, because there is x in the denominator. And it's that specific type that is easy. What is it called?
Cross multiplication.
What is it called, this equation? Rational, but what type?
Rational, but proportion.
Thank you. So let's cross multiply. So I get 3x equals 1. Therefore, x is?
1/3.
The other one is 1 over x equals -2 over 1. Cross multiply. -2x equals 1. X equals -1/2. I don't have to check anything. I did not employ that unsafe procedure.
I'm guessing an unsafe procedure is what I mentioned.
The unsafe procedure is when we square both sides.
Okay. So,
Or cube both sides, and we did not do that.
well, the thing I was getting at earlier was technically, theoretically, I think you could, instead of replacing it with that other type of equation, you could replace it with a rational equation right off the bat.
That's
right?
fine. We did that at the end. We had to do it at the end. I agree. You can do it from the beginning if you want, or you can wait and do it at the
I
end.
just thought I'd tell you and really everyone else here, hey, there's a quicker way to possibly do it.
We had to do that anyway.
Right.
Good. Absolute value equations. Absolute value equations. Ready? We already discussed it a few minutes ago, but we didn't write it. So let's go back to the simplest possible type of equation that we can encounter with absolute value. Okay, same idea, everything the same. I'm asking myself, find numbers whose distance from 0 is exactly 3 units. Which numbers? Exactly 3.
3 and -3.
That's it. X equals 3, x equals -3. So let's look at more sophisticated examples. Let's say 68 on page 186, and we have 3. The absolute value of 2x minus 1 equals 21. What do I do?
I want to say it's 3, but I'm not sure.
Okay, so let's write that. Note, never distribute.
Okay. There's a reason I said I thought I might be wrong. There's a reason I didn't say, yeah, you definitely should distribute.
Let me explain why. The absolute value bars are not grouping symbols. Remember when we looked at inequalities That's why I love writing on paper, because I can go back. How would I have done that with a board, right?
So instead of 3 times the whole thing, it's really just 3 times 2x.
So remember what I said here when I crossed it out here? And I said you can't touch the absolute value. It's untouchable. And here, remember, you said, let's multiply both sides by 2 to get rid of the fraction. Absolute value?
Involve touching.
Untouchable. Exactly. Good. So the same thing, untouchable. 2x minus 1, totally untouchable. What do I do then? I can still clean it up, and I have to clean it up. Exactly. I will divide both sides by 3. So the left-hand side is 2x minus 1 in absolute value. The right-hand side is 7. I am back to the simplest possible situation. Brian, please. I'm trying to find numbers whose distance from 0 is exactly 7. What should these numbers be? What can I have in here? What in absolute value is 7? 7. What else can I have in here so that the absolute value is 7? That's it. So then these are the 2 options. 2x minus 1 can be 7, or 2x minus 1 can be negative 7. These are the only 2 options. Any questions? Any questions? And of course, it's not done.
You have to simplify from there.
Yes, I have to add 1. So this is 2x equals 8, therefore x equals. And this is 2x equals negative 6, therefore x equals. Now, if you have any doubts, you don't have to go back and check. But if you have any doubts, you could. Let's try. 4. 2 times 4 is 8. 8 minus 1 is 7. The absolute value of 7 is 7. 3 times 7 is 21. If you want to check negative 3, 2 times negative 3 is negative 6. Negative 6 minus 1 is negative 7. The absolute value is 7. 7 times 3 is 21. You don't have to check. We did not employ any unsafe procedure here. Okay, so I like to look at one more problem before we hopefully continue. So let's look at 101. It's recommended, so I want to solve it with you. Or maybe let's do 102 so you can do 101. They're pretty similar. So we are given the following. R equals the square root of a divided by 4 pi. And we're asked to solve for a. R is not the variable. 4 pi is a number. A is the variable. And now, of course, I'm going to ask you what type of equation is this? How do we call it? Is it quadratic?
Radical.
Say it again.
Radical.
Of course, it has a radical, right? I was just being silly. Good. How do I solve the radical equation? Say it again. Of course, because the index is 2. If the index were 3, what would I have done to both sides? Okay, perfect. So then the left-hand side is r squared. What about the right-hand side?
A over 4 pi.
Very good. I'm solving for a. What do I do to both sides to solve for a?
Multiply by 4 pi.
Awesome. So the answer is 4 pi r squared. Any questions for me? Any questions for me? Okay, so please, between now and Thursday, please finish up as many problems as you can from here in preparation for the test and for classwork. And I'm going to just give you an idea for 2.1 and then we'll stop and give you the work for today. So basics of functions and their graphs. Okay, so chapter 2. Yes, please. Any questions? Oh, I thought you raised your hand. Any questions from me before we move on? Okay, chapter 2. So in 2.1, let's just refresh our memory on functions, just for a couple of minutes. So let's say I have scenario 1, I have scenario 2, and I have scenario 3. In this bubble, this is a set for x. And this is another set, but it's a set for y values. And the same for all three. And let's say I have 3 numbers here, and let's say I have 3 numbers here. And I create a correspondence. Let's say this number corresponds to this number corresponds to this one, and this number corresponds to that. I will mimic in the second scenario, but I will connect them differently. I will do the same thing in the third scenario, and I will connect them differently. Okay, so let's analyze the first situation. I created a relationship that connects this number to this x value to this y value, and this x value to that y value. Is this a function?
Yes.
Yes, because I can show that each x value corresponds to exactly one y value. So this is called a function. Awesome. Let's look at the second scenario. Is this a function?
No.
No, because I show that one x value corresponds to 2 y values. So this is not a function. It exists. It's possible. It's called a relation. What about the third one? Is the third one a function? Remember, each x to only one y. Each x to only one y. Each x.
By that logic, yes, because those two have the same one, but each one just gives one.
Very good. So it is a function. In all 3 situations, this set is called
Domain.
Excellent. And in all 3 situations, this set is called
Range.
Awesome. Indeed. Very good. One thing I would like to mention, which comes in this chapter later, towards the end of the chapter. So this particular concept is not going to be part of the first test, but I want to say it because we have the pictures right here. There is a big difference between these two. This one, can I create now, let's say, I mean, in the range, can I create, if I want to, can I create, going backwards as this domain and this range, a function or not? Yes. So to this, it will correspond only one x. To this will correspond only, in this case, one y. To this x will correspond only one y. To this x, only one y. So the reverse will also be a function. This one, there is no discussion here. It's not a function. But what about this one? If I want to go back.
It's not symmetrical.
Right. So the difference is this first scenario is called one-to-one. One-to-one function. This one is called not one-to-one. By one-to-one, we mean also to each y, it corresponds only one x. Any questions for me? Yes, please.
Could the number 2, scenario 2 be also not 1-to-1, or would we just
We only talk about functions being one-to-one. We don't talk about relations being one-to-one. Very good question.